Alkanes are saturated hydrocarbons compound. Due to the presence of single bond only, they have a general molecular formula of CnH. To N+2, where N is the number of carbon atom present in the compound. The simplest alkane has a molecular formula of CH4. Alkanes are called paraffins because they have a little affinity towards a general reagent. In other words, alkanes are inert substances. They undergo reactions under drastic conditions. Each carbon atom in an alkane is an sp3 hybridized. Therefore, having a tetrahedral shape and a bond angle of 109.5 degrees. Properties of alkane. For alkanes, they have no color. Alkanes are lighter than water and have a lower density. Alkanes dissolve more readily in nonpolar solvents than polar solvents. Because they are nonpolar molecules, the melting and boiling temperatures of shorter chain. Alkanes are low, but as the number of carbon atoms in the carbon chain rises, the melting and boiling values of alkanes rise. Alkanes have low reactivity, strong acids, bases. Oxidizing agents and reducing agents do not react with alkanes. Alkanes are valuable as fuels because they burn and release energy in the presence of ultraviolet light. Alkanes will react with halogens such as chlorine gas and bromine water. Prefixes for organic compounds. This are named after the number of the longest carbon chain. Present. If it is one carbon atom is called meth, 2 is ith. 3 is prop, 4 is but, 5 is pent, 6 is hex, 7 is hept. 8 is oct, whilst 9 is non, and 10 is dec. Example, we have butane that's. It has for carbon atom present in it compound. You're going to be the highest IQ student. After watching this video to end, naming alkane compounds is easy to go with but become complex when there is a substituent. Example of these substituent is the halides. This example shows how bromide is bonded to the pentane compound. To name this, we first number the longest carbon chain forward and backwards. Then we choose the least number of which the bromine is on. For this is on the 4 and 2 carbon atom. So we take the number 2. It is the least among 4. We add the bromo to it as we name it. So the name for this structure will be 2-bromopentane. Was that easy and cool? Try naming this structure and leave your answer on the comments section, and don't forget to like, share, and subscribe for more interesting videos. How will you name this alkane when the substituent is 2? In this we have bromine and chlorine all as a substituent. The naming is the same as the previous one, but for this, we consider them alphabetically, thus letter B will come before letter C. So in naming this it will be bromo before the chloro. We first number the longest carbon continuous chain forward and backwards, then choose the least numbers for the substituent. For this, bromine is on the 1 and 3 carbon, so it be 1-bromo. But no need to say the 1, and for the chlorine is on the 2 carbon, so it's 2-chloro. Therefore, the name of this will be 1-bromo-2-chloropropane, or simple bromo-2-chloropropane. How will you name this alkane? Since the bromine is 2, we will say dibromo. We number again forward and backwards. For this we have 1-bromo and 2-bromo, so we name it as 1,2-dibromopropane. How will you name this one? This an alkane with an alkyl group as a substituent. An alkyl is an alkane which has lost one hydrogen. Alkane has the general formula of CnH to N+2, where N is the number of carbon atoms present. Alkyl also has a general formula of CnH to N+1. Without the alkyl group, the name would have been butane. But since we a substituent, we will go the same process of numbering the carbon atom and choose the least number of which the substituent is found, and for this is on the 2 and 3, but 2 is the least, so we take 2. The name then becomes 2-methylbutane. The structure can also be represented as this structure. That is in a condensed form, or this or that, all can be used and is the same. Isomerism of alkanes compounds. When we talks about isomerism, is simply define and know as two or more compounds with the same molecular formula, but different molecular structures. Example, we have a butane which has 4 carbon atoms in it. We can rewrite this as 2-methylpropane, which also has the same number of carbon as in butane but is only the structures that differentiated them from each other. This is what we then call as isomerism, and the product are called isomers. Example 2 is a pentane isomers. They all have 5 numbers of carbon atoms, but in general, their structures are different. Therefore, for the isomers of pentane, we then have 2-methylbutane and again 2,2-dimethylpropane as an isomers for pentane. Isomerism is of 2 types, which are the structural isomerism and the stereoisomerism. For the structural isomerism, it deals with different arrangements of a compound with the same molecular formula. Example is bromobutane, which has 4 carbon atoms, and a bromide as a substituent can also be restructured as bromo-2-methylpropane and 2-bromo-2-methylpropane. Again, structural isomerism can be either a chain isomerism, or positional isomerism or functional isomerism. For chain isomerism, it only talks about different in arrangement of carbon-to-carbon bonds, whilst positional isomerism deals with the position of functional groups and substituent on the longest carbon chain, and the function isomerism talks about the difference in type of functional group bonded or attached to that organic compound. For stereoisomerism, it talks about the arrangement of atoms in space. For that, we have the geometrical isomerism and the optical isomerism. Geometrical isomerism deals and elaborate the spatial difference of organic compounds and are of 2 forms. One is the cis and the other is the trans. In naming this, we just add the cis or the trans to it and pronounce it as usual. For this, it will be cisbutene, and that will also be transbutene. Now for the optical isomerism. It talks about the superimposition of 2 organic compounds and is a non-superimposable. Like the left and the right hand are the same but different positions. Thus how optical isomerisms are like for the chloroethanol. They are the same but can't be placed on each other. This is due to the different orientation of their functional groups. Before substitution of alkane can occur, there must be a cleavage or breaking of bonds of the substituent. Example, when chlorine is going into a substitution reaction with an alkane, then the chlorine, which is of its state as diatomic, will atomize to get a free gaseous chlorine atom with a free electrons to bond with the alkane. Thus what we called as cleavage of fission of organic compounds. And for this we have a homolytic and a heterolytic cleavage. For the homolytic, the break electrons are shared equally among the fragments, whilst for the heterolytic, the break electrons are pulled to one side of the cleavage. The one with the highest negative charge pulls the electrons towards itself than the other. This results as electronegativity of the species. Electrophiles are electron-deficient species that have a tendency to accept an electron pair from other atoms or molecules. Electrophile is a chemical species that accepts an electron pair and forms bonds with nucleophiles. Electrophiles are either positively or neutrally charged, also called Lewis acid, as they accept electrons. Electrophiles have a positive or partial positive charge, or they have an incomplete octet. Electrophiles are attracted to regions of high electron density. Examples of electrophiles include carbocations, carbonyl compounds, and positively charged metal ions. Nucleophiles are electron-rich species that have a tendency to donate an electron pair to other atoms or molecules. Nucleophiles have a negative or partial negative charge, or they have a lone pair of electrons. Nucleophiles are attracted to regions of low electron density. Examples of nucleophiles include anions, lone pairs of electrons on oxygen and nitrogen atoms, and pi bonds in unsaturated compounds. The effect of the sigma electron displacement towards the more electronegative atom, by which one end becomes positively charged and the other end negatively charged, is known as the inductive effect. This effect is a permanent effect and generally represented by an arrow on the bond. It is present in a sigma-sigma bond, unlike the electromeric effect, which is present in a pi-pi bond. The halogen atoms in an alkyl halide are electron withdrawing, while the alkyl groups have electron donating tendencies. If the electronegative atom, thus having missing an electron, or having a positive charge, is then joined to a chain of atoms, usually carbon, the positive charge is relayed to the other atoms in the chain. Example of the inductive effects are been represented on the above figures showing the direction of the effect.